This is Mr. Holsey for H Squared Sufficiently Understood Science, and today we're going to be taking a look at Apeman. In other words, trying to figure out how we can look at the periodic table and understand atomic structure. So let's take a moment and refresh ourselves on atomic structure and look at the different subatomic particles. If you haven't seen the previous video on atomic structure, we'll link it up in the corner. So we're going to take a look at the acronym PEN, protons, electrons, neutrons. So protons have a positive charge and have a mass of 1 AMU. Electrons have a negative charge and a mass of less than 1 AMU. Basically non-existent because they are waves of negatively charged energy. And then neutrons have a neutrally charged and have a mass of 1 AMU. Both protons and neutrons are located in the nucleus, while electrons are in the shell or cloud. So on the periodic table, you're going to be given tiles, and these have different numbers and symbols on them to help you understand exactly what's going on with your element, what its atomic structure looks like. So up here we have the atomic number, which represents the number of protons and electrons. The element symbol, which gives us a symbol for those elements. A lot of times you'll notice that the element symbol doesn't necessarily match how we spell it. That's because it is based typically off the Greek or Latin for that element. And so they might be a little bit different. When you're writing element symbols, make sure you look for the capital letter. That represents the beginning of a new element, and that's going to come in handy when we talk about balancing chemical equations. And it'll be followed by a lowercase letter. Now, this isn't AI, this is AL. When you see an I on the periodic table, it's going to be made very clear and will look like that. Then we have element's name. We'll have the element's name right there, followed by the atomic mass. So this atomic mass has a lot of numbers. And if you watched our previous video on atomic structure, I kind of explained this. But so the atomic mass for this, we're just going to say is 26.98. Now, when we discussed that, we talked about how electrons have basically no mass. And it's sometimes a common misconception that this 0.98 represents the electrons, and that's not true. So the atomic mass is only looking at the nucleus. And so when we're discussing this, basically when scientists came up with the atomic mass, they looked at a whole bunch of different atoms of that particular element and came up with an average mass for them. And the reason being is that sometimes elements will have more or less neutrons than what you would think. And so sometimes they'll lose a neutron, sometimes they'll gain a neutron, and it doesn't really affect it, but changes the mass a little bit. So let's figure out how we can find the amount of protons and electrons in an element using the periodic table. And to do that, we're going to use APE. And so APE stands for atomic number, which if we draw a little periodic symbol right there, we're going to use the atomic number, which is right here. It's typically going to be at the top. Sometimes it'll be located in different places, but it's always going to be a whole number. And so the number of protons, so the atomic number here is 6, And so number of protons is 6, and the number of electrons will be 6. So really easy. So, and the reason again for that is that protons are positively charged and electrons are negatively charged. So in a stable atom, you're going to have the same number of protons as you will electrons. So kind of once again, think about it like a battery. You're always going to have a negative side. You're always going to have a positive side. Now to find the number of neutrons is a little bit more difficult. With protons and electrons, you simply have to look at that number and you know exactly how many are there. But with neutrons, you got to do a little bit of math and rounding. And so we're going to use man, Apeman. And so it's the mass number minus the atomic number, which is going to be rounded to the nearest whole number, equals the number of neutrons. So we'll take, once again, that carbon, okay? And so my mass number, or my atomic mass, is 12.01. So I'm going to round that to the nearest whole number. And so my mass number will be 12. My atomic number, right here, will be 6. So 12 minus 6 gets us 6 neutrons. Now when I do this, I like to kind of write this a little bit differently. And I'll make it more like this. That way it looks more like a traditional math formula to make things a little bit easier to remember that it's going to be subtraction. So your mass number, which is going to be rounded. So if I have a mass, I'm just going to make up a number, 46.7, okay? So when I put in my mass number, I'll round that to the nearest whole number, and it'll be 47. Minus the atomic number, which is always a whole number, because it represents the protons, and those protons determine what element it is. So that doesn't change, and that will give me my neutrons. So let's do a little bit of practice on this. So we have nitrogen. So we're going to use Ape first, so Apeman. So if you remember, Ape means atomic number is going to be equal to the protons. Those protons are going to be equal to the electrons, because once again, like a battery, you have the same number of protons and electrons in a stable atom. So first things first, let's identify our atomic number here. And our atomic number is going to be 7. So very simple. I know that that's our atomic number, and that's equal to the protons, 7. All right. Then those protons are equal to the electrons, so it's 7. Now we got to use man, and that was the mass number minus atomic number will give us our neutrons. Okay, so let's identify our mass number. That's 14.007, and we're going to round that to the nearest whole number, so that's going to be 14. Okay, our atomic number is 7, so we're going to simply set up our formula really quick. So we have 14 minus 7 gives us 7. And so our neutrons, in this case, will be 7. Now you notice that they're all the same. That is not the case for all atoms. Okay, it is not the same for all elements. You will end up with situations where you're going to have more neutrons or less neutrons than protons. So you have to go through the whole process. You cannot assume that when you do ape that you'll have the same number of neutrons. You have to do ape and man to figure out what subatomic particles are there. Now, I said we could figure out the atomic structure with this. So I know that I have 7 protons, 7 neutrons, right? So there's my nucleus. But what about those electrons? Remember, I said that the valence electron configuration for the atoms that we're going to be talking about this year is 2, 8, 8, 18. So that's first shell, second shell, third shell, fourth shell, right? So I know that the first shell can hold 2 valence electrons. So I have 7 of them. So I'm going to create an orbital, and please excuse my drawing. I'm going to put 2 electrons in there. Okay? So I have this orbital. I have 2 electrons, but I still have another 5 I have to deal with. So I'm going to create another orbital. And that first shell can only hold 2, so I have to make a new one. The next shell can hold 8. So I'm going to put the remaining 5 in that shell. 1, 2, 3, 4, 5. And so now I know what that element should look like on the atomic scale, with 2 electrons in the first shell and 5 in the outer shell. And so this has 5 valence electrons. It wants to have 8. So this element is looking to actively bond. Practice again with potassium. So we're going to do ape. So atomic number. So let's locate our atomic number right here. And so that's going to tell us our protons and electrons. So our protons, 19. Our electrons, 19, because they are going to be the same once again. And now we got to figure out our neutrons. So we have a atomic mass of 39. So we're going to round that, 39.098. So we're going to round that to the nearest whole number of 39. And so we're going to do the math really quick. And what we're going to see is we have 39 minus 19, and that's going to give us 20. And so this is one of those cases I was just talking about where you're going to have different numbers of neutrons than protons or electrons. And so this will have a different number of neutrons. I'm not going to draw the atomic structure of this one, but you get the idea. I would put in those shells, and I'd be able to figure out what that should look like approximately. We're going to try with magnesium. So once again, follow along if you're still having trouble with this. So ape, atomic number equals to protons is equal to electrons. So our atomic number, 12, which is equal to our protons, equal to our electrons. Then we do man. We have 24.305. We're going to round that to the nearest whole number of 24. And we're going to do 24 minus 12, which will give us neutrons at 12. And we'll do one more. Hydrogen. Here's a case where you might see a little bit of difference in the tiles. So right here is our atomic number. Down here is our atomic mass. And so what we'll do our same thing, ape. So atomic number is equal to the protons, so we have 1, which is equal to the electrons, 1, and then our mass minus our atomic number for our neutrons, so man. So here's our mass, rounded to the nearest whole number, minus our atomic number, and it will give us 0. So hydrogen does not have neutrons. So that's all for today. This was Mr. Holsey with H Squared Sufficiently Understood Science. Please remember to like, share, and subscribe, and we'll see you next time.